Hello, Maurieo! In this video I'm going to look at reducing short measured lines for both height differences and horizontal distance. Generally with short lines, let's say up to 200 meters, there is no need to be too concerned about some of the corrections that we have to apply, as we can just pretty much deal with the situation as it occurs. So as long as we're fairly close to sea level and we're only using short lines, there's no need to worry about curvature and refraction or sea level correction, and for that matter projection corrections and those sort of things. Now granted, a lot of these are catered for in the instruments that we use anyway, so they are calculated, but we don't need to worry particularly about them, unless of course we're going for real super high accuracy. But in the general run of things, general day-to-day situation, there's no real need to worry too much about these things. So let's just have a look at the general situation. We're set up at a point A with our total station, and we are observing to a prism over a point B some distance away. We measure the slope distance in this instance and the zenith angle. We measure on two faces for accuracy. Now what occurs here, of course, is that, well, we either measure the zenith angle or its complement here, the vertical angle. If the zenith angles are between 0 and 90, they're angles of elevation, and if they are between 90 and 180, they're negative angles of depression. And the vertical angle can quite easily be worked out by just subtracting 90 minus the zenith angle, which will give the correct sign. Now we can see here that here is a horizontal line at the level of the instrument, and here's our slope distance here, and then we draw a vertical line down which creates a right angle triangle. So we are able to work out the difference in height from the instrument to the prism. And we've also got the slope distance, and from that and the zenith angle, of course, which we use to measure the difference in height, we can measure the horizontal distance between the 2 points, which is usually the distance that we want, although when we are very high we reduce it to sea level, and sometimes we can apply projection corrections. But as these are short distances, we're not too concerned with that. We're just looking at the basics. Now the horizontal distance can be found by multiplying S, the slope distance, times the sine of the zenith angle, or S times the cos of the vertical angle with the correct sign. Delta H, the difference in height, is equal to S cos the Z angle, or the zenith angle, in degrees, or S times sine of the vertical angle, also in degrees. So we just need to make a little note about that there, that there's also in degrees there. Okay, just tidying up that little letter there. Now with the horizontal angle, that's pretty much the end of the horizontal distance, that's pretty much the end of the matter. However, with the difference in height, we have to account for the height of the instrument above the mark A and the height of the target above the point B. Now the easiest way to do this is to just start at A and start with the with the height of A, and I'm just putting a little dot over the eye there, the height of A. So start with the height of A and add to that the instrument height, which will get us to this height here, the height of the instrument, or the level or height of the instrument. Then we go along a horizontal line, add on to that the difference in height, or subtract, whatever the case may be, and that'll give you the RL or the height of the prism. And then from that, subtract the height of the target or the height of the prism, and that'll bring you to peg A. So it's quite simple if you just follow a little diagram. So it's the height of B, which we're talking about here, the RL, or the height above a datum, usually sea level. HB equals HA plus the height of the instrument at A plus the difference in height from the instrument to the prism minus the height of the target or the height of the prism, and that will give us the RL, or the height above the datum, of B. Now this is referred to as trigonometric heighting. Trigonometric heighting, or trigonometrical heighting, depending on which how you want to say it, but I've got trigonometrical written on here. Trig heights is the jargon that we use. Did some trig heights, so please yourself. So now moving right along, we're going to just have a look at some actual examples of what happens here. So here I've just sort of drawn up a pseudo field book. So I've said we're at IB1, we're height of instruments 1.67, and we're going to IB2 and to IB3. Height of target is 1.74, HT 1.47, IB3. Now, if we are measuring these using slope distance, we would usually measure the zenith angle. And here's the zenith angle I've measured here: 86.52.10 on left face, 273.08.10 on right face. And I appear to have just left out the little. Oh, we're not cooperating here. Oh, here we go. So I've just left out the degrees, minutes, and seconds there, but my pen's not going to cooperate. Degrees, minutes, seconds, degrees over there. You never see these things until you're going through them like this. So there we go. So 86.52.10 on face left and 273.08.10 on face right. Now what we do is with these is obviously we add them to add them up, or sum them, and we should get somewhere close to 360 degrees. In this case here, I've got 360 degrees 0020. Now that's all very well. What we then do is that 20 represents twice the error, so we take divide it by 2, which is 10 seconds. Take 10 seconds off each one, so that would give us a zenith angle on face left of 86.52, and then we've got two slope distances there, so we just mean those: 164.472. Okay, now then we go and reduce that. So 164.472 is our mean slope distance times our corrected zenith angle 86.52 gives us a slope distance of 164.226, which I round up to the nearest centimetre, 164.23. Now delta H, and when I'm doing these ones, I tend to work out my delta H mark to mark, just so that they're easier to compare. So delta H is 164.472 times cos 86.52, which gives us the difference in height between the instrument and the prism, and then I've added the instrument height 1.67 and subtracted the prism height, or the height of target, 1.74, and that gives us plus 8.92, which I've written in here and reduced that down here. So that's how I would reduce it. I'll just go through this other one here. Face left, so this is an angle of depression, 93, 1650, 266, 43, 20. Again, we add them up, 360 degrees, 0 minutes and 10 seconds. Now they should all come to round about the same thing, so that 20, 10, that's fine. But if you suddenly got one that was quite a bit different to all the others, you might want to re-observe that, because that's probably indicative of an error or something like that. But 360, 0, 10, and then of course, so that's 10, so that's 5 seconds, half of 10 is 5 seconds off each, so that would give us 93, 16, 45, which we've put up here. And then we mean our distance, so our distance, slope distance, or distance, horizontal distance, 98.274, our mean, times 93, 16, 45, our corrected zenith angle. It gives us 98.113, which I've rounded to 98.11. And then delta H, 98.274 times cos 93, 16, 45. That's mark to mark, plus 1.67, our height of instrument, minus the height of target, 1.47, gives us negative 5.421, which I've rounded to 2 decimal places and put here as minus 0.42. So, yeah, that's just a little bit of a sort of a pseudo sort of what might happen in your field book, or part of a field book. Here's some things to contemplate. Typically the prism constant is dialed into the instrument, so we don't need to concern ourselves with the prism constant, and I explain that in a separate video and mention it in others. Curvature and refraction is usually in the instrument, but it's not significant for these small ones. It can be turned off, it can be set to 0 if you want to, so that you can do things. Typically sea level correction is not significant, particularly in and around some of the areas where we work, but in some of the higher areas it can be. Typically meteorological corrections are not significant. We sort of tend to work in a perfect 20-degree world, and I don't know, 1016 millibars, but some instruments do measure the pressure themselves, and you just need to key in the temperature and they take care of all those sorts of things. Note that most total stations, and this is, record the slope distance in zenith angle, but they show the horizontal distance in delta H, so you're able to read these horizontal distances and the differences in height, and you're able to actually read those directly from the instrument. So a lot of this stuff is done, although be aware that there are various corrections that are applied. And so you can get the zenith angle and the slope distance out, but generally you can get it there. So they're available if you need and needed. So remember that the delta H that the instrument's working out is the delta H instrument to target. Although when you do have in a robotic situation where you might have your instrument hooked up to a data recorder, it is possible to get real time or true heights out of them by dialing in the pole height and the height of the instrument and that sort of thing. So there you are. This is the very short lines, very simplistic, just your straight basically sine and cosine to work out your delta height, your increase in height, and your slope distance reduced to the horizontal. In another video we will look at applying the corrections for longer lines where some of these corrections start to have some significance and need to be applied in our everyday situation.